All right, afternoon, everyone. So we're looking on January 2025, question number 1. So it says an antacid. What an antacid is, it is a compound that neutralizes acid in the stomach. So an antacid tablet neutralizes stomach acid to produce salt and water. So that's what is happening. Maxine wants to investigate the effectiveness of 2 brands of antacid tablet, Gravitio and Justid. Define the term acid. So an acid is a compound that dissolves in water. If you want to talk, you can talk. An acid is a compound that dissolves in water to produce H plus ions as the only positive ions. All right, so that's what an acid is. And we have 2 types of salt. We have normal salt and acidic salt. It's asking us to define a normal salt. One little piece. Yes. Go find the pencil, please. So it's so a normal salt is anybody? So it's a salt formed where all the H plus ions from an acid is replaced by metal or ammonium ions. So a salt form where all the H plus ions from an acid is replaced by metal or ammonium ions. All right, so the active ingredients in Gravitio and that is sodium carbonate. So that's what we're using to neutralize it. A sample of this, the JO and the Justid was added to dilute hydrochloric acid. The volume of gas evolved was measured every 30 seconds for 240 seconds, and the results are shown in the table. And then the experiment was repeated using the other brand. So here are the 4-time intervals for the Justid. So when you get a diagram like this for you to read off, which is quite common in a chemistry exam, the first thing you have to identify is where are we increasing from? Are we increasing from top to bottom or from bottom to top? So in this case, we are increasing from bottom to top because this is 10 and this is 20. So that's the first thing we need to identify. The second thing that we would need to identify is the value of each of these boxes. The value of each of these lines, sorry. So we are going up by 10. So from 10 to 20 means we're going up by 10. So to find the value of each small box, it is what you're going up by divided by the number of lines. So we start at 10 and the first line is 0. So this is 10. So that's 0, 1, 2, 3, 4, 5, 6, 7, 8. So we are at 8. So this would be 9, 10. So it's 10 divided by 10. So it means that each small lines represent 1, in this case, 1 centimeters cubed. All right, ready? So we're going to read off these and then we'll put them in the table whenever they're ready for the table. So let's go. So at 60 seconds, the time, the volume would be, so it is right here, midway between these two lines. So this is 8, this would be 18, and this would be 19. So at 60 seconds, it would be, so at 60 seconds, it would be, yes. So at 60 seconds, it would be 18.5. Then at 90, we have, so we have 20, 21, 22, 23, 24, 25, 25.5. Then at 150, we have 35, 36, 37.5. And at 40, we have at 120, sorry, we have 41. Anybody have any questions? No, in a table, this is the only one that has a solid line. Now in a table, each of the quantities must have the same number of decimal points. So although this is 41, we will have to put 41.0. Do we have any questions?
No questions from me, miss.
So here they're asking us to insert. So 60, 18.5, 18.5, 90, 25.5, 150, 37.5, 37.5. Me not follow what them do, cause them not follow them own rule. So 41.0. So it says using the axes provided on page, using the axes provided on page 7, plot a graph for the data obtained for adjusted in table 1. The graph for Gravisio is already been plotted for you. So that's what we're doing right there. So this is a rate of reaction question. Just take a picture of the table. No, that's fine. All right, so before we plot a graph, the first thing we have to do is to ensure that we know what we are plotting, right? So we're gonna ensure that we know what we are plotting. We need to know the value of each small box before we plot, so it's something similar. So here we're going up by 5. So it would be 5 divided by the number of small box. The number of small box between the 5 is 10. Yes, 0.5. So on the y-axis, we're going up by 0.5 centimeters. On our x-axis, we are going up by 30. We may need to know it when we're reading off the points. So to plot the graph, it won't be a problem for us because it's going up in the increment that we're actually measuring the time in, but that's fine. But in case we need to read off a specific value, then 30 is what we're going up by, divided by the number of small boxes, 10. So we're going up by 3 on the x-axis. So we're going to plot our graph. I'm gonna send a picture. 1 second, let me take back a picture so I can plot these. Or if somebody can take the picture and give them to me, that's fine too. All right, let's go. So we look and they have used a dot and a cross for the brand, for one brand. So in graph, we can only use dot and a circle or a cross. So in this case, because they've used dot and circle, I have to use a cross. So the ones I'm going to be doing, putting them in a cross. So the first one is 0, 0. So I'm using a cross to plot that. Then I have 30. 30 is 10. So I'm going to put my cross right here. Yes, half box. 60 is 18.5. So we're going up by 0.5. So 2 box would be 16. 2 boxes from 16, 17. 2 boxes from 17, 18. So 18.5 would be right here. No, I'm not steady, so that's why it's a bit. So 90 now is 25.5. So the first small box after 25 is 25.5. 120 is 120 is 32.5. So 32.5 is right here. Then I have 150. 150 is 37.5. 180 is 40. 120, 110, sorry, is going to be 41. 41 is right here. And then, yes, 1. In a pan. All right, so remember what we want to figure out is, so the purpose of this is to figure out which one of them is a better antacid, right? One little bit, yes. So turn off the TV here for me, please. Thank you. So I want to figure out the effectiveness of the two brands. So when both of them react, both of them are producing carbon dioxide. So the one which is most effective, we're going to say that one produces more carbon dioxide. Are we clear? So I don't know what the question is asking, because honestly, I first made the question. I don't even know what question it is. All right. Are we clear on that? So based on my graph here, which one of them is most effective? Hmm? Why nobody not talk to me?
Miss the one that they plotted.
Okay, so the brand they plotted. All right, so both of them produce carbon dioxide. Both of them end at the same point in time, because here the Gravasio ends at 47, sorry. So it ends at 47. So the reaction both ended at 210, right? But the difference is that this one produces, we know the reaction ends because we have a horizontal line right here. Right here is where my X should be, not over there. So let me rub out this one. My entire line gone. And because we have two things there on the graph, we're gonna label this just Shiva, I think, or Jessica. I don't know. I'm gonna go back. All right, let's go. Using the Gravassia graph, deduce the volume produced at 135 seconds. So again, this is where our value on the X is significant, and it says use dotted line on your graph to show how you obtained your value. So remember, we're going up by 3 on the y-axis. We're looking for 135. So we're looking for 135. So we're going to count the 3 until we get to 135. So we start at 120. This line here would be 123. This would be 126, 129, 132, and this is 135. So this bright line here is where the 135 is. So you're going to draw your broken line from 35 they're not steady. Definitely not a surgeon here. And it cuts the graph at the first line after the 40. So what volume is that? What volume is the first line after 40?
40.5.
40.5. Thank you. So it'll be one line for the broken line and then one line for the correct reading of. So it is so it's 40.5 centimeters squared. Using your answer from B, so using this answer 40.5, calculate the number of moles gas produced at RTP for Gravasio for the reaction at 135 seconds. So remember that the gas produced is carbon dioxide, right? And I'm looking if they give us the molar volume anywhere, and they have not. So what's the molar volume at, I'm not seeing it. What's the molar volume at RTP in centimeters cube? Using centimeters cube because the volume is in centimeters cube.
It's 24,000 centimeters cubed.
Good, 24,000 centimeters cube. So we're going to use the formula number of moles is equal to volume over molar volume. So the volume is 40.5 divided by 24,000, which is equal to 1.69 times 10 to the third power to the negative 3 power. And the answer is in moles. Write a balanced equation with state symbol for the reaction between hydrochloric acid and sodium carbonate. So sodium carbonate is Na two CO3. I would say 1 second. Just checking to say, so active ingredients in that. So I'm assuming that. So we can write solid or aqueous for the state of matter. It's not telling me if it is an acid, if it is a liquid or it is a solid, because we can have the antacid in the solid form and we add water. So you can use whichever one you want to use. I'm gonna use aqueous. Because if I water them add it's still gonna be aqueous. So I'll use AQ here. Plus 2 HCl. All acids are aqueous, so I'm going to be using HCl, AQ. I'm gonna get 2 sodium chloride. Plus water. Water is a liquid and CO2 gas. Determine the number of moles of sodium carbonate that's reacted at 130 seconds, right? So we have the number of moles of carbon dioxide that produce at 135 seconds. So we're going to use this number of moles of carbon dioxide and the mole ratio to calculate the number of moles of sodium carbonate. It's there. So the mole ratio is 1 mole of sodium carbonate equal 1 mole of CO2. No, I don't have one, start with the known first. So let me rearrange this. So we know that 1 mole of CO2. It's in the fridge in one bag, and don't call me again, please. Thank you. 1.69 times 10 to the negative 3. Because it's a 1-to-1 mole ratio, we know that it's going to produce the same number of moles of sodium carbonate. So the number of moles would be 1.69 times 10 to the negative 3 mole of sodium carbonate. Anybody have any questions? No? Using your answer from B6 on page 8, calculate the mass of sodium carbonate that reacted. So we'll have to determine the molar mass. So the molar mass is equal to 2 sodium. 2 sodium is in the compound, so 2 times 23, plus it has 1 carbon, 1 times the mass of carbon, which is 12, plus 3 times the mass of oxygen. And if my memory serves correct, it's 106 gram per mole. What is 6 plus 48 plus 12? Yeah, 106. So the number of moles that was formed is this. So we're going to use the formula. Number of mole is equal to mass divided by molar mass. So if we rearrange this equation, the number of moles times the molar mass is equal to mass. So the number of moles is the 1.69 times 10 to the negative 3 times the 106. What? I don't know. Somewhere here, so. 1.69 exponential negative 3. Anybody work it out? I got 0. 179.
That's what I got as well, miss.
Right. From the graph obtained in the investigation, Maxine suggested that Justid is the stronger antacid. To state whether you agree with Maxine and give a reason for your choice. Do we agree with her? Do we agree with her? We're gonna say no, we don't wanna eat. Which one of
Miss,
them
which
is
one is
better
neat that?
acid? See the graph here? Huh? Which one is a better antacid? Why is it better?
Because
Because it
more carbon
produces more
dioxide was produced.
respiration time.
All right, so this one is a better antacid. So because it produces more carbon dioxide, what does that mean in terms of sodium carbonate? Would it have more or less sodium carbonate?
More.
Ravasi has more sodium carbonate than Justid. So from my graph, that one has, let me just line this up so you can read what's on the line. Produces more carbon dioxide, but remember the carbon dioxide is not the antacid. The antacid is the sodium carbonate. So because it produces more carbon dioxide, it would mean then that the Gravasio had more sodium carbonate than the Justid. Clear?
Yes, miss.
All right. So this is what we have not done. This is a solubility question. This is January 2024. I'm thinking if memory serves correct. So Marcus was asked to design an experiment to investigate how the solubility of potassium nitrate varies with temperature. It is known that potassium nitrate is soluble in water but not soluble in pentane. Why is it soluble in water? Everybody's supposed to like sing this, like sing it, because we do this so often. Can we sing the response?
All nitrates are solid.
No, that's not the reason. Would I sing the answer?
Because the polar
Because it is
Polar?
the water is
Miss
polar.
water is polar and
So
potassium
the
is an ionic compound.
so the
So the slightly positive end of
so the
water.
positive potassium ions will be attracted to what?
The nitrate.
Positive potassium ions will be attracted to the partial what? Partial negative end of the water. The negative nitrate ions will do what?
To the partial positive end of water.
One of them will be attracted to the partial negative, no, positive end of the water. So why is it not dissolving in pentane? The pentane is nonpolar, so it cannot bond with the potassium and nitrate ions. Yeah, may I say all of that? All right, so once you're explaining why any ionic compound dissolve in water, you must talk about the polarity of water and saying that the partial and its partial negative end. We can't say the negative end of the water. So the partial negative end of the water and the partial positive end of the water. Clear?
Yes, miss.
So the procedure that Marcus used to carry out the experiment to investigate the solubility. So can somebody define solubility? I'm not sure if the question asks for solubility. Anybody remember the solubility? Solubility is the mass of solutes dissolved in 100 grams of water at a specific temperature I don't know if they want that, but me just ask. So exactly 100 centimeters cube of distilled water was measured and poured into a clean, dry 250 centimeters cube beaker. The beaker with the water was weighed and the mass recorded. So we're recording the mass of the beaker and the water. While maintaining a temperature of 10 degrees Celsius, solid potassium nitrate was added slowly with stirring until no more dissolved. So we would be able, because we know the weight of the beaker and the water, we will be able to determine what mass of potassium nitrate dissolved at 10 degrees Celsius by taking this new weight, right? Clear? Of the beaker, the water, and the potassium nitrate, and minusing that from the mass of the beaker and the water. Is that clear? So here it says, here, the mass of the salt solution was weighed and the mass recorded. So remember that the mass of the salt solution would be the mass of the beaker, the water, and the salt. Here in this step, I would have already determined the weights of the water and the beaker. So if I want to find the mass of the salt, what would I need to do? Subtract this weight here. So let's say this is the weight at B minus the weight at A. Clear?
Yes, ma'am.
You have to understand before you can do the question. So it says the experiment was repeated with 6 different 250 centimeters beaker while maintaining temperatures of 20, 30, 40, 50, 60, 70. All right, so again, you're weighing some stuff, so we will have to figure out the value at each small reading. So we're going up by, what value are we going up by? Going up by what, class? From 150 to 140, what's the difference?
10.
We're going up by 10, and we're going to count the number of spaces. So
10
start
degrees
at
Celsius.
140. So we weigh this. So start at 140. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm not take for granted so I know say it. So we're going up by 1 gram. Clear? Clear?
Yes, ma'am.
Right. So we're at 10. 10 degrees Celsius. I'm not reading them off. I don't know. Are you able to see them to read them? Can you read them? All right, so again, look, we're increasing. So increasing from left to right. So here is where my arrow is. My arrow is pointing. I get a nice little ruler. This look like it's a point right now. It don't look like it's a point there, so I cannot draw a straight line to save my life. Let's use the highlighter to see if we can get one better answer. That look like it, right? It look like the bright line, right? So that would be 42, 44, 46, 146. Clear?
Yes,
But
miss.
so 10 is 146. Anybody can read off the next one?
This
20,
148.
148. All right. So for this question, we do not need to calculate solubility because here's why we don't need to calculate solubility. Solubility says is the mass of the solute dissolved in 100 grams of water at a specific temperature. No, they are using 100 grams of the water. So whatever mass dissolves, whatever mass of solute dissolve at different specific temperature, that is the solubility because they're using 100 grams of water. Clear? Clear?
Yes, miss.
Clear? So whatever mass of solute dissolve based on the definition, mass of solute dissolve in 100 grams of water, because we're using 100 centimeters cube of water, the same thing as 100 grams of water. I do not need to calculate the solubility. Whatever mass of solute dissolve, that is the solubility. Just saying it again. So let's go. 10 of 46, 20, 30 is what? 143, looks like to me. 143?
153, miss.
153, sorry. 153. 40 is what? 40. 160. That would be what? 160 what?
Sure.
160 what?
3.
Why may I have 120 yes again? 20 is not, 20 is 148, sorry. 50. 169, it looks like to me. 60. Like 190, 246, 196. And this one would be 219. So 60. How much the 60 was? 60 is 195. No, 196. And then 70 is 119, 219. Clear?
Yes, miss.
X. All right, so for each of the temperatures shown in figure 1 on page 5, in the table, recording table 1, the corresponding mass of the beaker and salt solution. So here we have the original mass. So the original mass of the beaker and the water is 100 grams. So we're going to put in the mass of the salt solution and the mass of the salt solution. So what would be the mass of the salt that would be formed right here? How did we say we're going to get it again?
Subtract the mass of the beaker and water from the mass of the beaker and the salt solution.
Mhm. So let's go. What's the mass for 30? That would be
43,
43. Next one.
53,
Next one.
59,
59,
Next one.
86,
86. Next one. 109, right?
yeah.
Yes, miss.
Okay. I need this picture. Mhm. So in plot a graph, before we work it out, we need to figure out the value of each small box. What's the value of each small box on the y-axis?
1.
On the x-axis?
1,
It would be still 1. So 10 is 36. So this would be 35. So 36 would be right here. Let me use that cross because 20 is 38. 38 would be the third small box from 35. 30 is 43. So 41, 42, 43, the third small box from 40. 40 is going to be 53. Third small box from 50 is 53. 50, and believe me, somebody have to actually sit down in the exam and them have one ruler. So when you mark question 1, you have one ruler where you actually use to measure the line. I mark question 1 year and I'll never go back. It's way more money than the rest of the question, but it's too much work because it must accurate. You have to check them for accuracy. So 59, so nobody thinks you can just randomly put it on the box. No. The chief, very meticulous. She go check it. If it off by nothing, you're going to lose the marks. If you don't have the number of accurate points. So there's actually a ruler. You can zoom in and you can count off and show on the actual measurement. So don't play with that. 60. Where the graph stop? 70 is where it stop, right? So 60 would be 59. No, I'm just plot 50 as 59. So this is 86. So 2 small box from that is 86. 86 is 1 box from 85. All right. Remember mine I got so accurate because I use my hand. Yeah. And then the next one would be 109. 2 small box from there would be 109. I plot one nice, take a smooth little curve, something look wrong with one of them balaya. Let's check that. 59, 53. All right, so I'm gonna think this one though, this not going in my curve because I realize that this one looks a little off, right? So I'm gonna put that in my curve. Because it's not going with my trend. So I cannot draw. Here we go. All right. That's my curve. So what do we notice about solubility as temperature increases? So temperature is increasing. What do we notice about solubility of potassium nitrate? Describe how solubility of potassium nitrate varies with temperature. What's happening? As temperature increases, what's happening to the solubility?
It increases also.
So as temperature increases. Andrea, carry my laptop charger for me, please. This a dead quickie. Determine the solubility in grams per 100 dm cubes of potassium nitrate at 65. So we're going to find 65 on the graph, draw a broken line and read it off. How long does it run at oven? So you cook and you not time. Come, put this under there. So determine, so we find 65 and read off. So 65 is here. So this is 65 right here. So that's 65 and it goes all the way up. So we can read off that exactly what would my Y value be. What's gonna be my Y value? What's gonna be my Y value?
95.
95. $95 gram per 100 gram of water. Use your answer in E2. So using this 95 gram of potassium nitrate in 100 grams of water to calculate the mass of potassium nitrate that will be precipitated out of the solution if it is cooled down to 35. So we need to determine the solubility at 35. So we're going to go on the graph again, read off the solubility at 35. So 35 is going to be this right here. This look like 35. This look like for me 2 small boxes from 50. So that would be 48. So the solubility at 35 is 48. So that means that when we cool it, so at 65 is 95 grams that is dissolved in the water. 35 now has only 40 grams that's dissolved in 40 what? What am I saying?
48 grams, man.
48. So it would be, so I'm gonna write that 35 equal 48 gram per 100 gram of water. So if we cool it, it's going to be 95 minus 48, which is equal to 42 plus 5, 47 grams. Clear?
Yes, miss.
Calculate the concentration of moles per dm cube of a saturated solution of potassium nitrate at 35 degrees Celsius. So moles per dm cube. So we know the mass that dissolve in 100 at 35, and we said that was 48. So 48 grams of KNO3 dissolve in 100 grams of water, right? So before we get to that, 100 grams of water is the same thing as 100 centimeters cube, right? So what they want us to find out is how much, in terms of moles, how much would be in 1,000. So before I go to convert from mass to moles, I'm gonna just say how much mass would be in 1,000 centimeters cube. So X grams of that is in 1,000 centimeters cube. So we're going to cross multiply to find X. Clear? So 48 times 1,000 equal 100x. We want to get x by itself. So we're going to divide both sides by 1,000, by 100, sorry. So my answer is going to be 480, right? Right? So that's the mass that would form a saturated solution, but they want the concentration in moles per dm cube. So I'm going to calculate the molar mass of KNO3. So it's 1 potassium 39 plus the mass of nitrogen, which is 14, plus the mass of 3 times 16, which is equal to, I think 101 if memory serves correct. 39 plus 48 plus 14. 101 gram per mole. So number of mole is equal to mass divided by molar mass. So number of mole is equal to 480 divided by 101. So I'm going to get 4 point something moles. 100, turn off the stove, please. I don't know where you cook and watch. 4.75 mole. Clear? Per dm cube. Make it cool, little. It burn? Make it stay then. Any question?
No, miss.
All right, so this is not on my list of things to do, but because we're doing solubility, let's just do, Vashel, you good?
Yes, miss, I'm okay.
So I'm taking it to my exam that I did in 2006. I'm gonna stop taking it to my exam, not you? No. Paper 2. So it's another solubility question. However, this time they are not using the mass of water to be 100. So we'll have to calculate the solubility. Clear?
Yes, ma'am.
Yes, miss.
So I think in this question, they gave us a formula for the solubility. Yes, they did. But if they didn't give you a formula, all right, make work with the formula. So this is the formula for solubility, right? This off because they don't have to give it to you. You're supposed to know it. So it's the mass of solute divided by the mass of water multiplied by 100. That's the formula for solubility. So solubility is the mass of solute dissolved in the mass of water it dissolved in times 100. That's the formula for solubility. Clear?
Yes, miss.
All right, let's go. The following procedure is used to determine the solubility of X in water at various temperature. In experiment 1, table 1, 2 grams of X is added to 4 centimeters cube of water in a boiling tube. The tube is heated while storing and the water bath and stirred in a water bath until all of X dissolve. The solution is allowed to cool and the temperature at which X first appear is noted. So that's where, so you dissolve it and you cool it now to see where the saturated solution is formed. So that's how they can tell you the temperature, right? So in this case, they are heating it above the, so in the last experiment, what we were doing is we added until no more dissolves. No, this one they add until all of it dissolves at a high temperature, and just as then they cool it down until when the first crystals start to appear and record the temperature. So it's two different experiments that we can do to determine the solubility. So at which crystals of X first appear is noted. Experiments 2 to 5 were carried out using 2 grams of X, but in each case, different volume of water as shown in the table. The temperature at which crystal X appears are shown below. So again, we have to work out the value at each small box. So we're going up by 1, and we're looking at how we're increasing. So we're increasing from bottom to top. Very important, we don't assume that. So this right here, so going up by 5, and we have 5 small spaces. So 5 divided by 5 is what? 5 divided by 5 is what? 1. So the first one is 91. Then the second one is 57. It's kind of hard to read, so I'll just read them. Then the third experiment, we have 44. Based on my site. Then we have 32. And then for the last experiment, we have 26. 26. So we're going to calculate the solubility. So it's 2 divided by 4 times 100. This is gonna be 50, right? 2 divided by 8 times 100 is going to be 25. 2 divided by 12 times 100, 2 divided by 12 times 100 is going to be 16.7. So I'm going to go back up and put 0 for all of them. 25.0. And then this would be 2 divided by 16. So this is 12.5. 12.5. 2 divided by 10. So this is 10.0. So I'm adding the 0.0 because in a table, all the values must be expressed to the same number of decimal points. Clear?
Yes, miss.
So I'm not going to actually plot this graph. So the purpose of this was to show you what they could ask you. So I'm not plotting the graph. Let's read to see if they ask any additional question other than, so deduce the solubility from the graph. So we did that a while ago. Says calculate the volume of water required to just dissolve 2 grams of X at 60 degrees Celsius. So this one is different from the one we did earlier. So I'm gonna plot the graph. I'm not going to plot the graph. Let's look on an arbitrary. I'm gonna just plot something just for argument's sake. So I'm not doing the question, I'm sketching a graph. Clear? Can we appreciate that?
Yes, miss.
Yes, because I don't want to waste time plotting the graph. We have lots of other graphs to plot. So let's say for argument's sake. All right. I did not take the picture. I'm just gonna plot, somebody take the picture here for me, please. Where you gone? Question. All right, so we're gonna use this solubility graph just for argument's sake, right? So remember, the solubility tells us the mass of solute dissolved in 100 grams of water. So this is not the question, but this is a graph. So what we would do is read off from our graph. So I'm gonna use the solubility for Y for this graph. And I remember it just, all right, let me see if we have one question like this. I'm gonna use this graph instead, since it's already plotted. So it says, figure 2 on page 3 shows the solubility curve for two substances X and Y. Uses information to answer the following question. Which of the two substances has a greater solubility at 10 degrees Celsius? No, it does not ask us to do that. It's asking us a similar question to the one that we did. So we're going to ask it, what mass? So I'm going to retype a question. I'm going to answer that. So we're going to answer. So if you're taking notes, we're going to answer what mass of X, no, hold on, what mass of water would 2 grams of X be dissolved in at 60 degrees Celsius? So that's the question, right? So we find X on this graph. So X is here. We're going to find 60 and read off 60. So it's one small box above 10, above one, the bright box after 10. So for this graph, we're going to actually have to work out what each small box represent. So we're going up by 5 and 5, 5, 10, 15, 20, 25. So 5 divided by 25 is going to be 5 divided by 25. Each small box is going to be 0.2. So this would be 11. So the big box from 10 would be 11, the bright box, the bright line, and then one small box would be 11.2. Clear? Everyone's clear? I got 11.2. Any question how we get the 11.2? Are we clear on how I got the
Yes,
11.2?
Yes, miss.
Good. So 11.2. So it says what mass of water would X be dissolved in to be, at 60 degrees Celsius? 2 grams of X. So at 60 degrees Celsius, it is 11.2 grams. So at 60, 11.2 grams of X is in 100 grams of water. That's a solubility. So we want to know how much 2 grams of X, water 2 grams of X would be dissolved in. So 2 grams of X would be dissolved in X. Clear? X grams of water. Everyone is clear how we do that? Or we use the solubility formula. The solubility formula says that, what does it say? The mass of solute. So the mass of solute divided by the volume of water times 100. That's the solubility formula. So in this case, we have the solubility, right? And we have the mass of solute, but we don't know the volume of water, so we solve for the unknown. Or we can cross multiply here, like we did. So let's work out that first. So this would be 2. So when you cross multiply, it would be 2 times 100. I don't have my pen, so 2 times 100 is equal to 11.2x. So we want to get x by itself, so we're going to divide the 2 times 100 by 11.2. So my answer is 17.86. So I get 17.86. So here we know the solubility is 11.2. So I can't write. That's my biggest problem with this thing here now. Oh my God. All right, so here we are. So the solubility is 11.2. Based on the formula, the mass of the solute is 2 divided by the volume of the water, which you don't know, which is X, times 100. Same thing. So we're going to carry X over here. So it is 11.2x. So we multiply what's at the top. So 2 times 100 is equal to 200. And we want to get X by itself. So we're going to divide both sides by 11.2. 14, the answer is right, 17.68. Let me get that 6 from 86. That's the answer. So 200 divided by 11.2 is still going to give me 17.86. Clear?
Yes, miss.
So that's solubility. I'm now look on no more solubility question. Do we have any questions on solubility?
Oh, miss.
I want more hour before we take a break. Let's hope this question is fun that we're doing. Okay, so this is last year June's paper. Sodium thiosulfate solution. And they give us the formula, so they're very, very nice. Reacts with dilute hydrochloric acid. The formula for hydrochloric acid is HCl to produce sodium chloride solution, sulfur dioxide, solid, and water. So they're actually telling you exactly what's happening, right? So somewhere, actually, I'm familiar with some bits of this question. They're asking you to write the formula for the reaction, write the balance equation for the reaction. So we're going to start there. Give me a second to find my pen. Sodium thiosulfate reacts with hydrochloric acid to form sodium chloride, water, sulfur, and sulfur dioxide. So when putting the state symbol, although it never asks that, sulfur is a solid, water is a liquid, sodium chloride is aqueous, sodium thiosulfate is aqueous. So I'm gonna balance the equation. Na2 means we have 2 sodium on the left, so we're gonna put 2 in front of sodium chloride. So 2S, we have 1S in sulfur, 1S in sulfur dioxide, so we're good there. 3 O's, so we have 1 O in water. And 2 O's in sulfur dioxide, so that's 3 O's, so that's balance. So look on the H's, we have 1 H here, 2 H on the right, so we're going to put 2 in front of HCl. Then that would mean we have 2 chlorine, and we already have 2 chlorine in 2 NaCl. So we're balanced. To investigate the effects of temperature on the rates of reaction, Paul performed different experiments using sodium thiosulfate and dilute hydrochloric acid. For each experiment, the same volume and concentration of sodium thiosulfate and dilute hydrochloric acid were added, but at different temperatures. So in this case, the factor that they're investigating would be what factor would they be investigating for the rates of reaction? Sorry, unmute, but I didn't hear what you said.
Change in temperature.
So since temperature is the only thing that they're changing, the factor on the rates of reaction that they would be investigating, and them tell you the effects of temperature, right? So the temperatures were measured at the start of the experiment, and the thermometer readings for experiment 3 to 7 are shown below. So again, we have to work out the value that we're going up by. What value we're going up by? 1. Then we count. So the first one is 0, 1, 2, 3, 4, 5. 1 divided by 5 means we're going up by 0.2. So we're going to read these off. So experiment 3 would be what? 3 would be what? 14.0. Experiment 4 would now be what would be the temperature for 4? What would be the temperature at experiment number 4? Hello?
20.25.
What we're going up by, Michael? And that's why I don't think it redundant, but tell me what we're going up by. We are go up by?
0.2, miss.
We're going up by 0.2. So this would be 20. This would be 20.2. So this would be 20.4. And midway between 20.4 and 20.6, what do we have there?
20.5.
20.5. I that said it, said, Michael? I'm sure I never that me. That's what you said?
No, miss.
Okay. Next one would be what? Experiment 5.
27, miss.
0.0. Next one.
33.0.
Next one.
35.5.
Everybody see we got 35.5. And that's why we need to work out the value of each small boxes. We can't take it for granted that we know. All right, so there are the temperature readings. We read them off. So it says define the term rates of reaction. What's the rates of reaction? The rate of reaction is the change in concentration of a product or reactant or that per unit. And them rate of reaction is a popular question, number one. And most time they ask for the definition. Says the change in concentration of product or reactant per unit time at a specific temperature. Clear?
Yes, miss.
Describe a test and state the observation that can be used to confirm the presence of sulfur dioxide gas from the reaction. So this is a qualitative test. So testing for SO2. What do we use to test for SO2? Acidified
Acidified potassium permanganate.
Or acidified potassium dichromate.
dichromate. All right, so if we use dichromate, the observation would be what?
Orange to green.
And I'm going to change the color of the ink. So if the test we're using is going to be, acidified potassium permanganate, what would we use? What will I use? What's the observation? Sorry. I'm brain blank out.
Purple to colorless.
All right. Determine the mass of sulfur dioxide produced when 50 grams of gas was collected at RTP. So we want to calculate the mass of, so we can move from volume to mole, and then from mole to mass. Clear? So from volume to mole is going to be number of mole is equal to volume over molar volume. The molar volume at RTP is 22,400. So 50 divided by 22,400 gives me 50 divided by 22,400. I got 2.23 times 10 to the negative 3 mole. So that's mole, and I'm going to convert from moles to mass. So number of mole is equal to mass over molar mass. I need to determine the molar mass of SO2. So it's 32 plus 2 times 16, which is equal to 64 gram per mole. So if I rearrange this equation, number of moles is equal to mass times molar mass. Mass is going to be equal to number of moles times molar mass. So 2.23 times 10 to the negative 3 times 64 is equal to 0.143 gram. Clear? Claire?
Yes, miss.
Yes, miss.
Here is a table, them I ask it to work out some stuff. Table 1 records the temperature reading for each of the following, for each of the experiments shown in figure 1 on page 4. Table 1, the effect of temperature on the rate of reaction. So we're going to put in the temperature reading. So we have 14 divided by 20.5 for experiment 27.0. Then we have 33.0. Then we have 35.5. Girl, picture perfect. All right, so then it says that we calculate to 3 decimal place the rate for each of the experiments, given that rate is 1/t. So 1 divided by 40 is equal to
0.025.
0.025. Yes, you're working them out. Give me them then.
0.042. Miss, that is for the 24.
0.042.
0.067.
When I'm sure, I'm not in my room yet. I'm not in my room yet. And then what we have here, 11.
0.091. 0.100.
0.100. All right, so that is it. Then they're gonna ask us to calculate. No, done that. We are using the axis provided on figure 2.7, plot a graph of rate versus whatever. So this time I'm not going to do any work. You're gonna do the work. So I'm gonna show you the axis because in chemistry, you never ever have to find a scale. They generally give you the scale in most cases, or they give you, in most cases, they give you the scale or a part of the scale. So this is the scale. I'm going to put up the graph. So take a picture of the table and then you're going to plot the graph for me. Because I'm going to do the exam tomorrow. Definitely not. Not tomorrow, Friday. Yeah, the picture perfect. Ready? We have this picture. We have the data. We have the information from the table.
Yes, miss.
Okay, so this is the scale. I'm going to just zoom in a little so you can just copy the scale. And I tell me something another graph. Find one quick and fast. Rub out one from the maths them one that I practiced last week. And let's get it. So when you plot the graph, the graph shapes like a smooth curve. So we would record, we would connect a smooth curve through the lines. And then the last question says, using the graph you plotted on page 7, explain how the change in temperature affects the rate of the reaction between sodium thiosulfate and hydrochloric acid. So as temperature increases, the rate of reaction also increases. So that's it for that. So We are resuming. We're doing titration questions. Stop the recording here.